Okay, so in this video we are introducing basic object types in R. This is a very fundamental topic, and I guess it's one of the main tasks you have in the beginning of learning R to understand what different object types exist and why they are practically relevant. To put the whole thing into perspective, remember again the quote of John Chambers that we counted before, who said that everything that exists in R is an object, and everything that happens is a function call. Now, we already learned a bit about functions in one of the previous sections. Now we will deal with the more general concept of an object. You might ask yourself, why do we need to distinguish between different object types in the first place? Well, the reason is that functions are doing different things depending on what objects you're giving them as an input. So, for instance, adding up numbers is different than adding up words. The latter, in some cases, might not even be possible. But that already indicates that in order to understand what the functions you are calling in R are actually doing, you need to have a solid understanding on what you apply these functions to. And therefore, understanding the different object types in R is of utmost importance. Now, fortunately, in R, there are only very few basic object types you need to know about. Of course, there are more complex types, and we will encounter a couple of them in later sections, but these are usually natural modifications of these basic types. So if you want to understand something more advanced, like a table like data frame, that is actually not that difficult because it's just a modification of one of the most fundamental types, namely the list. But we will learn about this in a second. The most general type of an object in R is definitely a vector. So to better understand this, you can think of it that all objects that exist in R, so everything that exists is an object. But we can distinguish here between vectors on the one hand and null on the other hand. But you will already see here that null is a very particular basic object type. So we are not dealing with this in more details here. More important is the distinction of the different subtypes of vectors. Here, on the one hand, we have atomic vectors, and on the other hand, we have lists, which sometimes are also called generic vectors. The big distinction is that atomic vectors only comprise of elements of the same type, and lists can comprise of elements of different types. But we will delve into this in more detail a little bit later. But for the sake of having an overview, you should anticipate already that atomic vectors can be of a different subtypes. So there can be logical values, like true or false. There can be integers, like whole numbers, like 1, 2, 3. There can be doubles. Doubles is basically the same as decimal numbers, like 0.1, 1.0, 2.9, etc. And then there can be characters, like words or tokens, like one or hello, things like that. What distinguishes them from others are the quotation mark at the beginning and the end of the token. Then again, there are more advanced types of vectors, like factors or data frames. But we'll learn about them at a later point of time. And the good thing is, once you understand these basic object types, like atomic vectors, lists, and the different subtypes of atomic vectors, it's actually not that difficult to learn these more advanced concepts whenever you need them in practice. Please also note that in this figure, I haven't included functions because we have discussed them already before. But of course, they are also a very important element in R. But for now, let's first focus on atomic vectors and their different subtypes, and then we wrap up this section by dealing with lists. So let's start with atomic vectors. The important thing that distinguishes atomic vectors from other kind of vectors is that they are composed of objects of the same type. So mathematically, you can think of atomic vectors as as sets of objects. So an atomic vector contains one or more objects. These objects need to be of the same type. Otherwise, we wouldn't be talking about atomic vectors. Now, because atomic vectors can contain objects of a certain type, and all these objects are of the same type, we usually say that the atomic vector as a whole is of the same type as its elements. And by doing so, we can distinguish between four different types of atomic vectors. In practice, if you have an object and you don't know what type of vector it is, you can use the function typeof. We will learn about that practically in a second, but before that, I want to anticipate in a little bit more detail what the four subtypes of atomic vectors actually are. So the most important ones are the following. On the one hand, we have logical values. In R, they are called simply logical, and in fact, there are only two options, true or false. Missing values sometimes are considered logical values, but that doesn't really matter in practice. When do you encounter logical values? Usually only as a result of a logical operation, like a test of whether 4 is greater than 2. Well, the result of this test is obviously true. The result of a test like is 2 bigger than 4 would be false. That is when you usually encounter logical values, and that is actually quite frequently in practice. The second type are whole numbers. In R, these are called integers. A whole number in R is always followed by the big letter L. So if you want to create a whole number 1, you need to write 1 big L, or 2 big L, or 100 big L. Why is that? Well, you can read about this in the tutorial. It has some historical reasons, and it has to do with the predecessors of R in terms of a programming language. But aside of this, a little bit counterintuitive behavior when it comes to its definition, integers actually behave more or less as you would expect. We usually encounter them when we're counting something. So for example, how many elements are actually in that vector, then you usually get a whole number. Or if you're dealing with some kind of data, like for example, years or population size, something like that. This is where you encounter whole numbers or integers. The third type is quite related. It's called double, and it's actually nothing else than decimal numbers. Again, the term double refers to double precision vectors, so it's a little bit counterintuitive, but actually for you in practice, it's only important that double actually denotes any decimal number. So it's basically every number with a decimal sign as a dot, so like 2.0, 0.8, minus 7.5, something like that. Here, keep in mind that 2.0 counts as a decimal number, so as a double, but 2L counts as an integer. For you as a human, these two elements might be completely equivalent, but for the computer they are not. So there is a difference between 2 and 2.0. Nevertheless, I would say that in practice, doubles are the standard number you will use. In most of the cases you're dealing with something, doubles are much more frequent than integers. Nevertheless, both of them are very important. Now, the fourth type is what we as humans would call letter or words. In R, this object type is called character. Actually, characters do not need necessarily be words. They can contain all kinds of tokens. The only important thing is that they begin and end with quotation marks. Actually, they can begin or end with double or single quotation marks, but these quotation marks at the beginning and the end of a string are what make it a character in the sense of R uses it. So 2 written with a quotation mark at the beginning and the end counts as a character, not as a whole number or a double, but as a character simply because of the quotation marks at the beginning and the end. It's more obvious for things like hello or vec1, things like that, where we would naturally speak of words or characters. But what is really determining whether something is a character or not in R are the quotation mark in the beginning and the end. And these 4 subtypes of atomic vectors, so to speak, These are actually the most important major types of atomic vectors that you need to know in practice. Everything else is more or less built upon these types, so it's very important to distinguish them and to learn how to deal with them in practice. And the best way to do so is usually to just play around a little bit with them. So if you want to create an atomic vector that only contains a single element, that's quite easy. You actually just write down the single element. So for instance, to create an atomic vector of the type character that only contains the element hello, you just can write down hello. So you see this down here. Obviously here we haven't assigned a name to this object, so it's a little bit difficult to handle it. But we can verify actually to whether we're really dealing with a character by using the function typeOf that I've mentioned before. And if we execute this, we get the information or the confirmation that we are indeed dealing with a atomic vector of type character. So if you want to create an atomic vector with more than one element, you can use the function C, which stands for concatenate. And we can create here, for instance, an atomic vector. We might also assign a name to it, here tvec, and we might create an atomic vector with the two decimal numbers 4.6 and minus 102.4. If we execute this and we call the function typeOf on tvec, then we actually get the confirmation that we are dealing with an atomic vector of type double here. Now, when we talk about vectors, one important thing that often pops up is the length of the vector. The length of the vector can be assessed using the function length, and the length of tvec is, as you might have guessed, 2. So the length of a vector always corresponds to the number of elements that are in this vector. And as a side note, if you check the type of the length of the vector, you actually see that this is of type integer. I already mentioned at the beginning that counting stuff usually leads to the use of integers in R, and assessing the length of a vector is nothing more than counting actually the elements in this vector, meaning that the output of the function length is always a vector of type integer. Now we can use the function C also to concatenate vector or atomic, more than one atomic vector themselves. So for instance, we have our vector tvec here, which contains 2 numbers. Then let's say we have another vector, tvec 2, and let's say it contains the string hello here, and another string like this. Now, this vector now is obviously of type character, and we can concatenate, nevertheless, the vector tvec and the vector tvec2 by using the function C and just putting the 2 vectors in there. And we might also assign a name to that. And we now have a full vector here. Now, this, you might be surprised in the first case that it actually worked to concatenate a vector that contains element of type double with that of a vector that contains elements of type character. Whereas I said in the beginning that the essential feature of atomic vectors is that they only contain elements of the same type. That's true, and if we assess the type of our new vector, tvec full, we actually see that it now is of type character, and that the first elements that were part of vector tvec are now transformed or coerced into character, into the character type. And this is because there is a hierarchy between these 4 elements that I said before. And the reason is that it is very easy to actually transform all double objects into characters because you simply add quotation marks to the beginning and the end, as you can see down here. But it is not straightforward to transform all character vectors into doubles, because if you just remove the quotation mark at the beginning and end of hello, you wouldn't end up with a viable number. So in this sense, character vectors are on a higher level of the hierarchy than doubles, because you can transform doubles always into characters, but not always you can transform characters into doubles. And the hierarchy actually goes like this. So at the very bottom are logical values, then there are integers, then there are double values, and at the top of the hierarchy are characters. And to understand why this is the case, we need to talk about a concept that is called coercion. Coercion is really about transforming a vector from one type into a vector into another type. So let's say, for example, we have a vector called vec1. And this only contains a single double. Now there is a family of functions, the so-called as functions and is functions, and these functions are used to test or to coerce a vector regarding its type. So the is functions always work like this: you write down is at a point, and then you can write down the type you want to test this vector for. So if we want to test whether vector 1 is of type double, for instance, we write is double and then vec1, press enter, and we get a logical value indicating whether this vector is actually of type double or not. If we would like to test whether this is of type integer, for example, then we write is integer, the name of the vector, and here we get a false indicating that vector 1 is not an integer. Why is that? Because I already indicated, if you want to create an integer, it's actually not even sufficient to write down vec1 equals to 1. So if we test this for an integer, we still get false. You actually need to write 1L. If you write down this, you actually see that if you print it, you still see only 1. But if you now test for integer, you actually see that now the test is true. Another way to transform or to create an integer would be to stick with our original definition of vec1, and then to transform it using one of the as functions. The as functions work as the is function. You write as dot and then the type you want to transform the vector in. And if you want to transform vector 1 into an integer, and we now check whether it's an integer for vector 1 int, we get it true. So this coercion basically always works. Obviously, if you try to coerce a vector into a vector type that doesn't work, you usually do not get the result you actually want to. So why it works to say, okay, we have as double to 1 point and enter here the string 1.5, we indeed can transform the string into a double, but this is not always the case. So for instance, if we have a character called 1.5 and we want to transform this into a double, we actually get a warning. So now there is a missing value introduced because R is not able to transform or coerce the string 1.5 written as words into a proper double. So in this case, what R does, it creates a so-called missing value not available, NA. Yeah? NA stands for missing value, and NA is a peculiar type in this sense that it can mimic different object types. So it's best to think as NA being outside this classification of logical values, double, integers, and strings, because there's actually a specific NA type for each of them. NA just indicates a missing element of a vector, and if a coercion fails, then this basically creates a missing value. The good thing in this case here is that you're getting a warning message that your coercion was not successful, be aware that there are also some counterintuitive behavior when it comes to coercion. So it is very important to be really careful when doing this. So, for example, what would you expect if we coerce the number 1.99 into an integer? You might think, okay, it actually rounds to the next integer close by, so you actually get 2. But what actually happens is that this as-integer function actually just cuts everything after the decimal point. So if you transform 1.99 into an integer, you actually get number 1. Similarly, for example, if we want to transform the function the number 99 into a logical value, it is not immediately clear what you actually get. So what you actually get is the value true. Now, why is that the case? Because basically true and false can be encoded as 1 or 0. But actually it works like this, that if you transform a number into a logical value, you get true whenever this number is bigger than 1. So if we write here as logical as 0, then you get false. If we write as logical 0.5, we get true, because that is a number different than 0. If you say as logical and you have minus 0.2, you get also true, because the number is different than 0. So basically every number different than 0 that you transform into a logical value results in true. Only the number 0 actually results in false. Now, it makes a little sense under the hood of R, but it's not very intuitive, so be very careful when you use this transformation. Also be aware that sometimes R functions transform their input automatically. So if we sum 2 and say 2 as an integer with 1.5, and we call it vec3, then the result of this will be double. So here R automatically applies the hierarchy that we encountered before, with double being on a higher place of the hierarchy than integers. That might also, in most cases it's useful. Sometimes it's also a little bit counterintuitive. So if you add 2 and true, and you then look at what the result is, we here get an integer, because integers are in a higher place on hierarchy than truth values or logical values. So we here remain on the level of an integer. And finally, if you add, for example, true plus true, you might wonder what this is. You actually still get an integer, and you get the number 2. Because when you make mathematical operations with logical values, true always counts as 1, false as 0. It's a good idea to read a little bit more about that in the tutorial. For now on, I think it's sufficient to keep that in your head whenever you're working with object types. And I recommend now to actually have a look at what we've learned so far, make a little exercise, and then have a look at the solution to the exercise again and check whether you actually understood well the concepts that we've discussed so far.